History has long taught us to admire the Greeks for their marble statues and profound philosophy, yet we have conveniently ignored the secret heartbeat of their civilization, the rhythmic clicking of bronze gears. I am Elias Untold Vance, and today, on About Untold History, we are stripping away the myths to reveal the metal beneath. Imagine a temple where doors open as if by magic, or a theater where mechanical figures enact epic tragedies, powered not by ghosts, but by the relentless precision of pneumatics and hydraulics. This was not the future. This was the reality of ancient Greece. We are uncovering a world where the line between nature and machine was perpetually erased by the minds of visionaries like Hero and Ctesibius. You are about to enter a lost technological epoch that science historians have struggled to piece together for centuries. Prepare to see the ancient world as you never have before, cold, calculated, and terrifyingly mechanical. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The story of Hellenistic automation does not begin with the machine itself, but with the profound intellectual evolution that occurred in the centuries following the conquests of Alexander the Great. As the Greek world expanded, crossing the boundaries of Egypt and the Near East, a unique cross-pollination of knowledge took place. The empirical observation of the Egyptians and the mathematical rigor of the Greeks merged to create an environment where the physical world was no longer seen as a static entity governed only by whim, but as a system of forces waiting to be decoded. To understand how the ancient Greeks built mechanical automatons, one must first recognize that their mastery was rooted in their obsession with geometry. For the Hellenistic engineer, a machine was simply a physical embodiment of a geometric proof, a tangible demonstration of logic in motion. In the workshops of Alexandria, the epicenter of this technological explosion, mechanics began to distance themselves from the traditional artisan class. They were scholars, mathematicians, and architects who viewed the manipulation of matter through the lens of pure logic. They identified that motion could be transferred, multiplied, and stored. They developed the fundamental components of classical mechanics: the gear, the pulley, the lever, and the screw. These were not merely tools for construction, but elements of a nascent language of engineering. The Hellenistic mind perceived the universe as a grand machine, and by extension, they felt empowered to replicate the behaviors of that universe within the confined space of a stage or a temple. This philosophical underpinning is crucial. The automaton was, in their eyes, a cosmic mimic. By creating a mechanical bird that chirped or a statue that poured wine, they were not just performing a trick. They were exercising human sovereignty over the forces of nature, essentially participating in the creative process of the gods. The role of mathematics in this genesis cannot be overstated. Figures like Archimedes, although often associated with siege engines, laid the groundwork for the structural physics required to sustain consistent, fluid motion. They understood the relationship between the center of gravity and balance, which allowed for the creation of intricate counterweight systems. This was the birth of the algorithmic approach to design. By mapping out a sequence of actions, such as a series of cogs turning at specific intervals, they were essentially coding the behavior of their machines. When we look at the ruins of these concepts, we see that the Greeks had begun to master the art of sequential logic. A machine designed to open a door when fire was lit on an altar was a logical loop. If X occurs, then Y must follow. This cause and effect relationship, stripped of its mystical facade, formed the bedrock of all future robotics. Furthermore, the environmental context of the Mediterranean played a decisive role in fueling these innovations. The reliance on water as a primary power source led to the refinement of hydraulic systems. Water, flowing at a constant rate, provided a predictable, reliable, and rhythmic kinetic energy that became the heartbeat of their mechanical theater. They were pioneers in flow control, developing complex valves and siphons that allowed for the regulation of speed and pressure. This was not just plumbing. This was the science of fluid dynamics applied to entertainment. They learned to harness the potential energy of falling water to trigger pulleys and release tension in cables, turning the inanimate into the animate. This mastery of hydraulic control essentially allowed them to create the world's first analog computers, devices that processed physical inputs and produced complex, programmed physical outputs. As we dig deeper into this history, we realize that the Hellenistic engineers were engaged in a form of intellectual rebellion. They were operating in a society where labor was traditionally performed by human or animal muscle. To replace that labor with the energy of water, fire, or gravity was a radical shift in perspective. It was the democratization of power. The automaton allowed for the spectacle to be independent of the fatigue or fallibility of a living performer. When a mechanical figure danced or a mechanical trumpeter played, it was a display of permanence in a transient world. These machines were designed to last, to repeat the same performance flawlessly for eternity, provided the water flowed and the gears remained clean. This desire for perfection, for a world that functioned with the reliability of a geometric theorem, is what drove them. It was a search for order in a chaotic universe, and for a few golden centuries, they found that order in the precise, rhythmic, and awe-inspiring dance of their mechanical creations. The foundation they laid was so robust that it would influence the trajectory of scientific thought long after the golden age of Alexandria faded into the sands of Antiquity. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. To understand the mechanical revolution of the 3rd century BCE, one must focus on the life and work of Ctesibius of Alexandria. Often referred to as the father of pneumatics, Ctesibius was not merely an inventor. He was the primary architect of an entire branch of physics that had never been systematically explored before. His genius lay in his ability to perceive air and water, not just as passive substances, but as active mediums through which energy could be stored and transferred. While his original writings have been lost to time, his influence was so profound that it was recorded by later scholars like Vitruvius, Philo of Byzantium, and Hero of Alexandria. Ctesibius lived during a time when Alexandria was the intellectual lighthouse of the world, and his inventions represented the pinnacle of Hellenistic ingenuity, blending the abstract beauty of mathematics with the gritty reality of mechanical power. His most revolutionary contribution was the development of the force pump. Before Ctesibius, the movement of fluids was limited by gravity or the laborious effort of lifting buckets. Ctesibius realized that by using a piston within a cylinder, he could create a vacuum that would draw water upward and then force it out under significant pressure. This was the birth of the double-acting piston pump, a machine that would eventually become the fundamental mechanism behind firefighting equipment, irrigation systems, and hydraulic machinery for centuries. It was a masterpiece of design, incorporating leather seals, check valves, and precise cylinder fitting that allowed for continuous flow. This invention was not simply a tool. It was a conceptual triumph, proving that fluids could be forced to disobey their natural downward pull through the application of controlled mechanical action. Beyond the pump, Ctesibius delved into the world of pneumatics, studying the compressibility of air. He constructed devices that used air pressure to drive mechanical motion, often creating magic effects that would stun his contemporaries. One of his most celebrated creations was the water organ, or hydraulis. This was an incredibly complex machine where a water pressure-regulated air tank provided a steady, consistent flow of air to a set of pipes. Unlike a traditional wind-blown instrument, which was dependent on the varying breath of a human, the hydraulis was perfectly tuned and capable of sustained, powerful sound. It was the first time in history that a musical instrument was powered by an external mechanical force, turning the art of music into a feat of engineering. The hydraulics required a sophisticated understanding of pressure balancing and airflow regulation, demonstrating that Ctesibius could harmonize the chaotic nature of gas dynamics into something beautiful and predictable. His work extended into the development of highly accurate water clocks, or clepsydra. While simple water clocks had existed in various forms for millennia, Ctesibius took the concept to a new level of complexity. He utilized a feedback system, a float that regulated the inflow of water, to ensure that the timekeeping mechanism remained consistent regardless of the water level in the source reservoir. This was an early implementation of a feedback loop, a concept that is essential to modern automation and control theory. His clocks were often paired with elaborate mechanical displays. As the hours passed, intricate figures would emerge, birds would sing, or stages would shift, providing a constant automated show that mirrored the passage of time itself. These clocks were more than just timekeepers. They were symbols of the Hellenistic obsession with capturing and measuring the invisible flows of the universe. The legacy of Ctesibius is not just in the specific devices he built, but in the precedent he set for the mechanization of reality. He demonstrated that the physical forces of the world were not insurmountable obstacles, but variables that could be manipulated through the application of science. By codifying the principles of pneumatics, he provided a manual for later generations to follow. When Hero of Alexandria later expanded on these concepts to create even more elaborate toys and engines, he was merely building on the foundation that Ctesibius had laid down in his workshop centuries earlier. The Age of Water was, in essence, the era when humanity first truly began to master the environment through engineered flow. Ctesibius transformed water from a simple necessity of life into a versatile source of kinetic energy, setting the stage for a mechanical civilization that looked at the world not with fear, but with the curiosity of an engineer seeking to solve the puzzle of existence. His work remains a testament to the idea that with enough ingenuity, even the most fleeting elements of nature, air and water, can be tamed and harnessed to create works of enduring mechanical wonder. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. If Ctesibius provided the mechanical vocabulary of the Hellenistic age, Philo of Byzantium, writing in the late 3rd century BCE, became the author of its most elaborate dramas. Philo was an engineer of the spectacular, a man who understood that mechanical innovation was not just about utility, but about the profound emotional impact it could have on an audience. His work, Pneumatica, serves as one of the most vital windows into the ancient mind's obsession with engineering artifice. Philo realized that the principles of air pressure, siphons, and hydrostatic equilibrium could be used to create an immersive theater, a world where the environment itself appeared to come alive. His machines were not merely functional. They were stagecraft of the highest order, designed to provoke awe, disbelief, and a sense of divine mystery in those who witnessed them. The mechanical theater of Philo was characterized by its complexity and its use of hidden logic. He specialized in creating banquet automata, self-pouring wine vessels, mechanical puppets that danced, and fountains that defied gravity. One of his most iconic designs featured a vessel where the liquid level remained constant regardless of how much was poured, an illusion created by a sophisticated airtight reservoir system and a precision-tuned siphon. These were the party tricks of the elite, designed to demonstrate the owner's wealth and their mastery over the laws of nature. By using these devices, the host was effectively presenting a theatrical environment where nature was subservient to art. It was a clear departure from the purely functional engineering of his predecessors. Philo was interested in the psychology of the observer, in how a machine could disrupt the spectator's reality and make them question what was real and what was artificial. Philo's contributions to weaponry and siege engineering while often separate from his automata, were rooted in the same pursuit of efficiency and mechanical dominance. He was a master of torsion springs, studying the elasticity of hair, sinew, and metal to create catapults of unprecedented power. This duality, the ability to build both a delicate, singing mechanical bird and a devastatingly powerful torsion engine, highlights the broad scope of the Hellenistic engineer. To Philo, the mechanics of a bird's wing and the mechanics of a tension-based launcher were two sides of the same coin. They were both governed by the laws of geometry and physical force. He treated every machine as a problem to be solved through the meticulous application of mathematics. His writing style, which focused on clear, step-by-step instructions, suggests that he was deeply committed to the transmission of knowledge. He was building a legacy of technical literacy that he hoped would endure. Perhaps the most fascinating aspect of Philo's work was his application of the cipher to create magical effects that, to a modern eye, look remarkably like early robotics. He designed elaborate fountains that would start and stop their flow based on timed mechanisms, or vessels that would fill themselves only when a certain amount of liquid was removed, creating a perpetual motion illusion that fascinated the ancient Pharaoh's world. These were programmatic machines. By setting the diameter of the siphons and the height of the water reservoirs, Philo was effectively coding the behavior of the fountain. He was teaching the ancient world that complexity could be managed, and that behavior could be predicted and replicated through deliberate design. The Theater of Wonders was not just a collection of cool gadgets. It was a manifestation of the belief that the universe was a complex, beautiful, and ultimately logical system that could be mastered by the human mind. Ultimately, Philo of Byzantium was the bridge between the theoretical mechanics of Alexandria and the widespread, practical application of automation across the Mediterranean. He moved the machine out of the workshop and into the center of social life. By documenting these devices so thoroughly, he ensured that the Theater of Wonders would not be limited to his own imagination. He taught the ancient world that engineering was a form of communication, a way to speak to the public, to entertain them, and to show them the possibilities of a future built on physical laws rather than just myth. His legacy is the realization that technology is fundamentally a tool for shaping human experience. Whether used to build a war engine or a wine-pouring doll, Philo's machines were designed to leave the observer forever changed, wondering just how much of the world was truly natural and how much was waiting to be redesigned by the hand of an master engineer. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. If Ctesibius was the inventor, and Philo the dramatist, Hero of Alexandria was the ultimate synthesizer of the Hellenistic age. Writing in the 1st century CE, Hero inherited the vast repository of mechanical knowledge gathered over the previous 3 centuries. His work, Automata and Pneumatica, represents the zenith of ancient engineering literature. Hero was a prolific author and a master tinkerer who treated mechanical design with the rigor of a scientist and the flair of a magician. His most iconic invention, the Automata, or Hero's engine, stands as the most potent symbol of ancient missed potential. It was a simple spherical steam turbine, a metal ball mounted on an axis with 2 bent nozzles that allowed steam to escape, causing the device to spin rapidly. This was the first recorded instance of steam power being converted into rotary motion, a concept that would not be formally realized again until the steam age of the 18th century. Hero's genius did not stop at steam engines. He was obsessed with the concept of the total spectacle. He designed mechanical theaters that could perform entire narratives without human intervention. By using a system of ropes, counterweights, and sand-driven timers, He could choreograph a complex, multi-act play where figures moved, doors opened, and light effects shifted in perfect synchronization. He understood that the secret to long-form automation was the master clock, a mechanism that regulated all other movements. In his theater, a large cylinder filled with sand slowly emptied, providing a constant, reliable force that pulled the ropes at specific intervals. This was a form of mechanical programming, where the sequence of the drama was physically hard-coded into the length of the strings and the weight of the sand. What makes Hero's work so compelling is his focus on the user interface and the magical experience of his devices. He often hid his mechanisms within architectural features, altars, temple doors, or ornate statues, so that the effects seemed to occur by divine will. One of his famous temple doors would open automatically when a fire was lit on the altar. As the air inside the altar heated up, it displaced water into a container, which acted as a weight to pull open the heavy doors. This was a classic application of thermodynamics. To the ancient observer, this was a miracle. To the engineer, it was a closed-loop system of physical laws. Hero took great pleasure in explaining the how behind the wow, effectively demystifying the supernatural and replacing it with the predictable beauty of mechanics. He was a scientist, but he was also a showman who knew that technology was most effective when it felt like a brush with the extraordinary. The Olympial and his other machines were not built as industrial tools, but their existence forces us to confront a difficult question. Why did this technology never lead to an industrial revolution? The answer likely lies in the socio-economic structure of the ancient world. With an abundance of slave labor and a society that prioritized philosophical inquiry over mass production, there was little incentive to replace manual labor with complex, costly, and fragile steam engines. Yet, Hero's work proves that the lack of progress was not due to a lack of talent or insight. The blueprints for the industrial age were already on the table. They were simply being used to build theater sets for the amusement of the elite, rather than to power the factories of the masses. Hero's legacy is a profound reminder that history is not a straight line of inevitable progress. He stood at the edge of a mechanical future, demonstrating that steam, air pressure, and automated motion were well within the grasp of human intelligence. His books were preserved, copied, and studied for centuries, serving as a blueprint for the engineers of the Renaissance, who would eventually rediscover these principles. Hero of Alexandria was the last giant of the classical era, the man who brought all the disparate threads of Hellenistic physics together and wove them into a coherent, brilliant tapestry of invention. He proved that even in the ancient world, the human mind was capable of dreaming of a world driven by fire and steam. A dream that, while dormant for centuries, would eventually ignite the modern world into motion. His machines were the silent heralds of a revolution that was destined to wait until the world was finally ready for it. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. If the automata of Hero and his predecessors were the software of their Hellenistic age, designed to entertain and mimic, the Antiquity mechanism was the hardware of unparalleled complexity. Discovered in 1901 by sponge divers in a Roman shipwreck off the coast of the Greek island of Antiquity, this corroded lump of bronze and wood has since been revealed to be perhaps the most sophisticated artifact of the ancient world. It is, by every modern definition, an analog computer. Dating back to the 2nd or early 1st century BCE, it contained a complex array of at least 30 interlocking gears, designed to track the movements of the sun, the moon, and the planets with astonishing mathematical precision. It was not a toy for a banquet hall. It was a scientific instrument of such advanced design that nothing of its equivalent sophistication would appear again for over 1,500 years. The mechanism functioned as an orrery and an eclipse predictor. By turning a hand crank, A user could move the gears to calculate the position of celestial bodies on any given date. It could account for the irregular orbits of the planets and the complex, varying speed of the moon's transit across the sky, a phenomenon known as the lunar anomaly. To achieve this, the engineers used a pin-and-slot mechanism, a masterstroke of mechanical design that perfectly modeled the elliptical motion of the moon. This was not a simple representation. It was a mathematical model translated into physical metal. It proves that the Greeks had moved beyond mere observation of the heavens into the territory of predictive modeling. They were not just watching the universe, they were simulating it. The implications of the Antiquity mechanism are staggering. It suggests that there existed an entire lost industry of precision instrument making in the Hellenistic world. Workshops filled with specialized tools, skilled bronze smiths, and mathematicians working in tandem. The gear teeth were cut with such uniformity that they suggest the use of a precision dividing engine, a device we previously assumed was a much later invention. The level of miniaturization, cramming 30 gears into a space the size of a shoebox, indicates a mastery of metallurgy and friction reduction that defies our traditional view of primitive ancient science. This was a piece of technology that required a deep, theoretical understanding of astronomy and trigonometry, as well as the practical ability to turn those theories into a functional, durable object. Why did this technology disappear? The mechanism remains an anomaly because we have found no other examples like it. Yet its very existence proves it was not a one-off miracle. It implies that similar devices, perhaps even more complex, were likely common among the academic elite of Rhodes or Alexandria, only to be lost to history through the degradation of materials like wood and papyrus, and the eventual cultural shifts that followed the decline of the Hellenistic world. It stands as a silent witness to a lost knowledge, a reality where the ancient Greeks possessed the capacity to engineer the cosmos on a desktop. It serves as a stark reminder that history is fragile. Technological breakthroughs can be forgotten, discarded and buried at the bottom of the sea, leaving behind only tantalizing hints of what humanity once achieved. The study of the Antiquity mechanism has forced us to rewrite the history of technology. It proves that the line between the ancient world and the modern is much thinner than we once thought. When we examine its gears through modern X-ray tomography, we are essentially looking at the great-grandfather of the mechanical watch and the electronic computer. It bridges the gap between the philosophical desire to understand the stars and the mechanical imperative to control time and space. The mechanism did not just track the planets. It organized the human perception of time, turning the infinite, swirling complexity of the heavens into a predictable, manageable, and tangible sequence of numbers. It was the ultimate ancient achievement, the capture of the divine order of the stars within the reach of a human hand. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. While the Greek mind was consumed by the theoretical and the philosophical, the Roman mind was defined by the pragmatic and the monumental. As the Roman Republic and later the Empire absorbed the Hellenistic world, they did not merely conquer territories. They inherited the technological secrets of the East. However, the Romans underwent a radical shift in how they applied this knowledge. Automation and mechanical precision were not viewed by the Romans as toys for the theater or objects of scientific curiosity, but as tools for governance, infrastructure, and military dominance. The Roman adaptation of Hellenistic engineering represents a transition from the science of wonder to the science of utility. They took the complex gears of Alexandria and the pneumatic theories of Byzantium and scaled them up to the size of the world. The Roman approach to engineering was built on standardization, where the Greeks might create a unique, singular automaton for a wealthy patron. The Romans developed modular systems that could be replicated across the vast expanse of their territories. They were the masters of mass production in the ancient world. Their aqueducts, roads, and siege engines were all products of a standardized mechanical philosophy. They adopted the hydraulic principles pioneered by Ctesibius and Philo and transformed them into the infrastructure of empire. The Roman water mill, for instance, used the same gear-driven kinetic energy as the Greek water clocks, but repurposed it to grind grain on an industrial scale, feeding the immense populations of Rome and her provinces. This was the transformation of automation from a theatrical gimmick into a vital economic engine. In the realm of military engineering, the Romans pushed the limits of the torsion engines they inherited from Greek innovators. They refined the catapults, ballistae, and onagers to a level of lethal reliability that defined Roman warfare for centuries. They utilized the same principles of physics and tension-based energy storage that were used in mechanical theaters to project heavy projectiles over hundreds of meters. By incorporating metal-bound wooden frames and sophisticated winch systems, they ensured that their machines were both portable and devastating. The Roman engineer, often a centurion or a specialized military architect, saw no difference between the mechanics of a clock and the mechanics of a siege engine. Both were systems of energy storage and release intended to achieve a specific, predetermined outcome. This shift to utility also saw the integration of complex engineering into urban life. The Romans were obsessed with the control of environment. Their public baths, fed by immense aqueducts and managed through complex gravity-fed systems and heating pipes embedded in walls, were marvels of hydraulic engineering. They were essentially large-scale pneumatic and hydraulic machines designed to control heat and water flow for the comfort of the public. The magic of the Greek temple door, which opened through the displacement of water by heat, became the standard heating solution for the Roman villa. The Roman innovation was in the scale. They were the first civilization to prioritize the mechanical improvement of the daily lives of millions, creating a level of comfort and sanitation that would not be matched for over a millennium. However, this pragmatic focus had its drawbacks. By focusing almost entirely on the functional and the imperial, the Romans inadvertently suppressed the more abstract and exploratory aspects of Greek science. The inventive drive that led to the anti-thera mechanism, or the steam-powered Gallipoli, was often sidelined in favor of the immediate needs of the state: the next road, the next bridge, the next weapon. Roman engineering became the bedrock of Western civilization, creating a legacy of roads and structures that still stand today. But it also signaled the end of a certain type of scientific dreaming. They solidified the mechanical techniques, ensuring their survival and spread across Europe. But they moved the focus away from the theater of wonders to the theater of order. In the Roman view, the machine was the ultimate servant of the state, a silent, efficient, and uncomplaining soldier in the service of the Roman peace. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The fall of the Roman Empire is often depicted as the point where technological progress stopped. But this is a profound historical misunderstanding. While the centralized state apparatus of Rome crumbled, the knowledge of mechanics did not disappear. It retreated into the shadows. The medieval period was not a dark age of intellectual inactivity, but rather an era of decentralized innovation. The knowledge of gears, levers, and hydraulics, once the domain of state-sponsored engineers, became the guarded secrets of monastic communities, localized craftsmen, and the nascent guild systems. The legacy of the Greeks and Romans continued to flow through hidden channels, waiting for the right moment to re-emerge as the foundation of a new mechanical world. In the monasteries of Western Europe, the tradition of mechanical timekeeping evolved. The need for precise prayer times necessitated the development of improved clocks, and it was in this quiet, meditative environment that the Virgin Foliate escapement, the breakthrough that allowed for mechanical timekeeping, was born. This was a critical step in the history of automation. Unlike the water-driven clocks of Ctesibius or the astronomical simulators of the Antiquity mechanism. This was a gravity-powered, rhythmic system of energy release. It was, in essence, the digital heartbeat of the medieval world. It marked a shift from the flowing, variable nature of water to the discrete, binary nature of the mechanical tick. This was a fundamental change in the human experience of time, shifting from fluid transition to granular sequence. Simultaneously, the development of water power in the rural landscape of Europe underwent a quiet revolution. While the Roman watermill was used for grain, the medieval millers adapted the technology to power fulling hammers, bellows for iron smelting, and saws for timber. They scaled up the application of cams, a simple mechanical component that translates rotary motion into reciprocating motion. By applying the cam to the water wheel, they achieved a level of automation that effectively replaced muscle power in heavy industry. This was the birth of the medieval machine age, where the landscape was dotted with wheels that never stopped turning. This widespread deployment of mechanical power was a precursor to the Industrial Revolution, occurring centuries before coal and steam took center stage. In the Islamic world, the preservation and advancement of Hellenistic engineering reached a golden zenith. Scholars such as the Banu Musa brothers, writing in the 9th century, took Hero's Pneumatica and pushed its boundaries further. They built trick vessels, automated fountains, and complex automata that kept the tradition of the Hellenistic theater of wonders alive. They were the bridge between the ancient world and the Renaissance. Their work was not just an imitation of the Greeks, it was an expansion. They added layers of complexity, refining valves, improving air pressure regulation, and introducing new types of mechanical linkages that had never been documented before. They ensured that the flame of mechanical curiosity remained bright in a world where the West was struggling to recover its footing. Ultimately, the medieval period was a time of internalizing and maturing the knowledge of the past. The engineering of the Middle Ages was less about the spectacular monument and more about the persistent machine. The technology moved from the stage and the temple into the factory, the tower, and the workshop. It became part of the daily rhythm of life, so integrated that it was often overlooked. The mechanical secrets were held in the tension of a clock spring, the rotation of a mill wheel, and the pages of carefully transcribed Arabic and Latin manuscripts. While the era lacked the centralized ambition of Rome, it laid the essential infrastructure for the future. It was a time of silent mechanics, where the gears of history continued to turn, unseen but relentless, slowly building toward the resurgence of the scientific spirit. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The Renaissance was not merely a rebirth of art and philosophy. It was a profound, systematic recovery of the mechanical past. As manuscripts from the classical era, those of Hero, Vitruvius, and Archimedes, were rediscovered, translated, and analyzed, the European intellectual elite experienced a shock of recognition. They realized that the ancients had possessed a level of technological sophistication that had been obscured for centuries. This rediscovery acted as a catalyst, igniting a hunger to not only replicate the machines of antiquity, but to surpass them. The Renaissance engineer, typified by figures like Leonardo da Vinci and Brunelleschi, became a hybrid figure, part artist, part mathematician, and part visionary mechanic. They viewed the machine as the physical manifestation of human reason, a tool to unlock the secrets of the natural world. Leonardo da Vinci stands as the quintessential icon of this awakening. His notebooks, filled with thousands of sketches of gears, flying machines, tanks, and automated lions, were not just artistic exercises. They were a rigorous, systematic attempt to map the mechanical possibilities of the universe. Leonardo understood that the principles of geometry, once applied to mechanics, could lead to infinite innovation. He dissected the mechanisms of the past, and reassembled them with a new understanding of friction, structural integrity, and material science. His work on the transmutation of motion, transforming linear motion into rotary motion, or vice versa, represented a leap in mechanical literacy. He wasn't just drawing machines. He was conceptualizing a mechanical vocabulary that would eventually build the modern world. Architecture during this period became the grand stage for mechanical innovation. Filippo Brunelleschi's work on the dome of the Florence Cathedral is a testament to this shift. To lift massive stone weights hundreds of feet into the air, he didn't just rely on manual labor. He invented a series of complex gear-driven cranes and hoists powered by oxen. These machines were triumphs of mechanical advantage. They demonstrated that the large-scale projects of the Renaissance required a new level of systems engineering. The coordination of power sources, structural support, and synchronized mechanical motion. The building site became a laboratory, proving that the abstract theories of the ancients could be scaled up to tackle the most daunting physical challenges of the day. The Renaissance also saw the convergence of printing technology and engineering. The dissemination of printed manuals, illustrated treatises on mining, ballistics, and hydraulic machinery meant that mechanical knowledge was no longer a guarded secret in a monastery or a guild workshop. It became open-source knowledge. This flow of information was revolutionary. An engineer in Germany could study a design perfected in Italy, iterate upon it, and publish the results. This cycle of documentation, critique, and refinement created a feedback loop of innovation that accelerated at an unprecedented rate. The machine was now a shared human project, a collective accumulation of knowledge that transcended borders and time. Furthermore, the Renaissance obsession with anatomy and biology bled into mechanical design. Engineers began to look at the human body as a machine, the pivot of a joint, the tension of a muscle, the lever of a bone. This biomechanical perspective allowed for a more organic approach to automation. They began to design machines that were not just rigid, industrial structures, but fluid, adaptive, and efficient systems. This holistic view of the machine as something that could breathe, move, and react like a living organism was a radical departure from the static, gravity-bound machines of the medieval period. The Renaissance was the era when the machine began to mirror the complexity of life itself, setting the stage for a future where the distinction between the biological and the mechanical would begin to blur. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. By the 17th century, the image of the machine had expanded beyond the workshop and the cathedral. It had become the metaphor for the entire universe. This was the era of the mechanical philosophy, a worldview championed by thinkers like René Descartes, Christian Huygens, and Isaac Newton. They moved past the mere building of machines and began to ask, what if the universe itself is a machine? This shift in perspective was revolutionary. If the cosmos was a grand, complex mechanism designed by a supreme architect, then it was, by definition, knowable, predictable, and, most importantly, subject to the laws of mathematics. The clockwork universes was the final realization of the mechanical dream that began in Alexandria, a reality governed by immutable logical rules. The development of the pendulum clock by Christian Huygens in 1656 served as the heartbeat of this new philosophy. By utilizing the isochronism of a swinging pendulum, the principle that its period remains constant regardless of the amplitude, Huygens transformed timekeeping from a rough approximation into a precision science. This was not just a better clock. It was a physical manifestation of the belief that nature operated on rhythmic, mathematical principles. The pendulum clock became the standard against which all physical processes were measured. If a machine could track the heavens with perfect accuracy, then the heavens must operate like a machine. This belief provided the intellectual confidence necessary for the scientific revolution to take flight. Isaac Newton took this mechanical metaphor and gave it a rigorous mathematical framework in his Principia Mathematica. By defining the laws of motion and universal gravitation, Newton provided the operating system for the universe. Gravity was the invisible linkage, the cosmic gear that kept planets in their orbits. To Newton, the universe was a vast system of masses and forces, all interacting in accordance with precise geometric laws. This was the ultimate expression of the mechanical philosophy. All physical phenomena, from the fall of an apple to the motion of the tides, could be reduced to mechanical interaction. The divine mystery of the cosmos was replaced by the beautiful, transparent logic of a massive, perfectly balanced clock. This mechanical worldview also revolutionized technology. Engineering was no longer a matter of craft or intuition. It became a branch of applied physics. Engineers began to use calculus to analyze stress, tension, and the efficiency of machines. The black box of ancient engineering, where a machine worked but the why was often vague, was opened. Now, every component of a device was analyzed for its mathematical efficiency. This rigor led to the development of higher precision instruments, including advanced telescopes, microscopes, and navigational tools. The ability to manipulate the physical world with precision grew exponentially because we finally understood the underlying laws of physics that dictated how the world reacted to our interventions. The clockwork universe was a triumph of the human intellect, yet it also carried a cold, deterministic weight. If the universe is a machine, is there room for spontaneity, for life, or for free will? This question would haunt the philosophers of the age, but for the engineers, it was an exhilarating realization. It meant that if the world was a machine, it could be understood, repaired, and even improved. This philosophy laid the bedrock for the industrial age. It provided the intellectual justification for the massive projects of the 18th and 19th centuries. The steam engines, the locomotives, the telegraph lines. By viewing the world as a clockwork system, humanity stopped being a passive occupant of the earth and became its active, mechanical master. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. The conceptual groundwork laid by the mechanical philosophy finally ignited in the 18th century when humanity mastered the ultimate force, steam. If the Hellenistic era was the age of water and the medieval period the age of the pendulum, the modern era was forged in the heat of the furnace. The transition from the hero's elapile, a scientific curiosity, to the industrial steam engine was a matter of scaling the mechanical philosophy into practical reality. The steam engine was the definitive machine. It converted heat, the most chaotic and intangible form of energy, into the controlled, linear, and rotational motion required for mass industry. At the heart of this revolution were innovators like Thomas Newcomen and James Watt. They faced a fundamental problem: how to transform the expansive force of boiling water into a consistent mechanical output. Newcomen's atmospheric engine was a crude but effective starting point, using steam to create a vacuum that allowed atmospheric pressure to drive a piston. However, it was Watt's refinement, the separate condenser, that changed the course of history. By cooling the steam in a separate chamber, the engine could remain hot, vastly increasing its thermal efficiency. This was the triumph of thermodynamic engineering. For the first time, a machine could work continuously without the massive energy loss of heating and cooling the primary cylinder, turning the engine into a reliable source of power. The impact of this cannot be overstated. Steam power decoupled production from the constraints of geography. Before the steam engine, factories had to be built next to fast-flowing rivers to harness water wheels. With coal and steam, they could be built anywhere. This triggered the rise of the factory system, the concentration of massive urban labor forces, and the birth of modern mass manufacturing. The steam engine became the prime mover of the Industrial Revolution, powering everything from textile looms and flour mills to the massive pumps that kept mines dry, allowing for the deeper extraction of the coal that fueled the fire in the first place. A perfect self-reinforcing mechanical loop. This era also saw the mechanization of transportation. The application of steam power to locomotives and ships transformed the world into a smaller, more interconnected space. The railway was not just a vehicle, it was a linear extension of the factory, a system designed to move materials and people with clockwork precision. The engineering required to build steamships and locomotives forced a new standard of metallurgical accuracy and material strength. The components, cylinders, pistons, boilers, and connecting rods had to withstand immense pressures and high temperatures, leading to advances in steel production and casting that pushed the boundaries of what was physically possible. As the machines grew in scale and complexity, the role of the engineer shifted again. They were no longer just building individual devices. They were designing interconnected systems. The steam engine necessitated complex networks of supply chains, logistics, and maintenance. It created a society that functioned like a machine, synchronized, efficient, and relentlessly productive. The steam engine was the ultimate realization of the clockwork universe as applied to human survival and progress. Fire, once a wild, destructive element, had been shackled by iron and brass, directed through pipes, and measured by gauges, turning it into the engine of modern civilization. We had successfully taken the ancient dream of fire-driven motion and scaled it to reshape the surface of the planet. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. While steam engines powered the muscles of the Industrial Revolution, a quieter, more cerebral revolution was taking place in the world of mathematics. For centuries, engineers had dreamed of machines that could not just transmit force, but process information. The path from the simple gear-driven adding devices of Pascal and Leibniz to the complex designs of Charles Babbage represents the shift from mechanical calculation to computational logic. This era marked the birth of the idea that a machine could follow a set of instructions, an algorithm, to perform tasks far beyond the reach of human mental arithmetic. Charles Babbage, the 19th century polymath, stands as the visionary architect of this new computational age. Frustrated by the high error rates in human calculated navigation and engineering tables, Babbage conceived of the difference engine, a massive, gear-driven apparatus designed to calculate polynomial functions automatically. His dream, however, went far beyond simple arithmetic. He envisioned the analytical engine, a machine that possessed what we now recognize as the fundamental components of a modern computer: a memory unit, which he called the store, a central processing unit, the mill, and the ability to accept programmed instructions via punched cards. The punched card system, famously adapted from the Jacquard loom, was a pivotal breakthrough. By using a series of holes in cards to represent logical instructions, Babbage effectively decoupled the hardware of the machine from its software. The engine didn't need to be rebuilt to solve a different problem. It just needed a new set of cards. This was the moment engineering transitioned from being a physical configuration of gears into a logical configuration of data. Babbage's design was fundamentally abstract. It was a physical realization of symbolic logic, proving that complex thought could be broken down into discrete mechanical operations. Working alongside Babbage was Ada Lovelace, the daughter of Lord Byron and a mathematician of extraordinary foresight. While Babbage focused on the mechanical engineering of his engines, Lovelace grasped the deeper philosophical potential of the machine. In her extensive notes on the analytical engine, she was the first to realize that the machine could manipulate not just numbers, but any set of symbols, be it music, logic, or art, provided they followed a set of rules. She saw that the machine could be programmed to create, effectively predicting the existence of computer science a century before the technology existed to build it. Her vision of a machine that could think according to human-defined patterns changed the nature of mechanical inquiry forever. The tragic reality is that neither the difference engine nor the analytical engine was fully completed in Babbage's lifetime. The mechanical tolerances required were simply beyond the reach of Victorian manufacturing. Yet, the failure to build these machines does not diminish their historical weight. They remain the most sophisticated mechanical blueprints of the 19th century. They serve as a bridge between the physical clockwork of the previous centuries and the electronic information age to come. They taught us that if a process could be described in words or equations, it could be performed by a machine. Babbage and Lovelace transformed the machine from a tool of power into a tool of intelligence, setting the stage for a world where logic, rather than just steam, would drive the evolution of technology. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey. We have traveled from the first bronze gears of the Antiquity mechanism to the dream of the analytical engine. This journey through history reveals a profound truth. The evolution of the machine is, in reality, the evolution of human thought. What began as an attempt to mimic the stars, to capture the divine order of the heavens in physical form, eventually became the tool that allowed us to decode the universe itself. We did not merely build machines. We externalized our own cognition. We turned our sense of rhythm into the clock, our labor into the steam engine, and our logical processes into the computer. The machine is not an alien force standing apart from humanity. It is our mirror, our memory, and our extended intellect. The legacy of the mechanical is the story of abstraction. Every step in this development, from water-driven theater puppets to punch-card logics, was an act of simplifying the complex. We learned to break down the natural world into smaller, manageable pieces: gears, levers, cams, and circuits. We learned that the universe operates in sequences, and by mastering those sequences, we could transcend the limits of our own biology. This mechanical literacy is the bedrock of modern civilization. It is why we live in a world of high-speed computation, automated infrastructure, and global connectivity. We are surrounded by the grandchildren of the Antiquity mechanism, devices so integrated into our existence that we have forgotten they are, at their core, manifestations of ancient dreams. However, this legacy is also a responsibility. As we move into an age of artificial intelligence and advanced robotics, the lessons of the past become more vital than ever. The history of the machine warns us that technology is never neutral. It is shaped by the cultures, politics, and philosophies of the time. The Greeks used gears for wonder, the Romans for empire, the Victorians for information. Today, we are tasked with deciding what our own machines will be used for. Will we continue to use them merely for efficiency? Or will we find in them a new way to understand our place in the cosmos? Mechanical philosophy was not a dead end of 17th century thought. It is an ongoing question about how we, as humans, interact with the physical laws that govern our reality. As we look to the future, we carry the mechanical ghosts of our ancestors with us. We see the influence of Babbage's logic in every line of code. We see the echoes of the steam engine in our energy grids. And we see the ancient quest to simulate the heavens in our space, probes, and supercomputers. The story of the machine is, at its heart, the story of human ambition, the desire to reach further, calculate faster, and understand deeper. It is the story of our refusal to accept the boundaries of the physical world. We are the species that builds to understand, and in building we have built ourselves into a new state of existence. The final sequence of this narrative is not written in metal or silicon, but in our continued quest for knowledge. The machines will change, evolve, and perhaps one day become unrecognizable to us, but the impulse remains the same. The human desire to capture the infinite, to turn the swirling chaos of existence into a predictable, beautiful, and functional sequence of reality. From the shipwrecked bronze of the Aegean to the digital networks that bind the globe, the gears of history keep turning. And as we turn the crank for the next turn of the machine, we are not just building the future. We are discovering, piece by piece, who we are. Don't forget to subscribe to the channel, follow us, and turn on the notification bell to stay updated with our upcoming historical journey.